We'll have the vision talk by Manish Pandey, VP Engineering, Synopsys. The talk is titled Unleashing AI/ML for Faster Verification Closure. Manish Pandey is a Vice President R&D and Fellow at Synopsys and an adjunct professor at Carnegie Mellon University. He completed his PhD in Computer Science from Carnegie Mellon University and a BTech in Computer Science from the Indian Institute of Technology, Kharagpur. He currently leads the R&D teams for formal and static verification technologies and machine learning at Synopsys. He previously led the development of several static and formal verification technologies at Verplex and Cadence, which are in widespread use in the industry. Manish has been the recipient of the IEEE transaction in CAD Outstanding Young Author Award and holds over 24 patents and refereed publications. Please join me to welcome Manish Pandey.
All right, am I audible? Shreya, thank you for the introduction. And it's good to be back here. Actually, after all the virtual events, it was finally great to have a live audience and kick it off. Okay, so the topic of my talk today is about intelligent verification. And in fact, ML and AI is truly revolutionizing verification technologies even today. It's not a thing of the future. And I wanted to talk, a bit about that, share some of what's happening in the industry, share some of what we have been doing, and and look to where the future lies. Okay. But first, actually, let's look at where this industry is going. And I think that over the last, this is barely visible here. Actually, over the last 6 decades, this exponential growth in transistor count is one of the driver forces of our industry. And going to 3 nanometer, 2 nanometer, possibly even 1.5 nanometer, it's pretty much a foregone conclusion. Already, actually, TSMC is going to get our chips tipping out. Their test chips already running at 3 and 2 nanometers. All kinds of exotic technologies, gates all around, and all kinds of devices stuff will be there. In terms of packaging, you have interposers with chiplets, 3D ICs. And so all of this really kind of gets us to the SysMore era where, we should soon be having actually 1 trillion transistors on a die. It's not too far, not too far in the future. Okay. Now, and this is what's enabling the consumer devices of today. This is what's enabling the gaming platforms, the medical devices, the IoTs. On the server side, we have the AI chips and the new processors, automotive, self-driving, changing out there. But if you take another perspective, with all of this growth in transistors, where are we with respect to better, sooner, and cheaper, right? Quality of results, time to results, and cost of results. Now, that tells a completely different story. Now, if you look at where the cost is growing from, as the number of transistors are growing exponentially, right, the cost of verification is also taking off a similar track. So in about 2020, mid to large size SoC cost about $300 million to verify. That's not a small number. And that number is expected to grow to about $600 million, actually, in another 3 to 4 years. I think if that pace continues, I think it'll soon start rivaling the cost of fabs. And then we know that that's not going to be happening out there, right? So something has got to give. If you take a look at, from a time perspective, right, verification time is again starting to dominate the total time of taping out a chip. So going actually from about, 2020, about 55% of the total time is dominated by verification, and this is expected to kind of grow to 80%, right? I mean, think about it. You're taping out a chip, or you're on a tape out a chip, and about 80% of the schedule is something that's going to be taken by verification. So if you look at the sooner, definitely that's not happening. That's not a trend going in the right direction. If you look at cheaper, definitely not. I think in terms of compute resources, in terms of the number of verification engineers need, in terms of the time. And for the most part, the number of bugs, per module or per 1,000 transistors. That has kind of stayed more or less constant. So definitely quality of results is something that's it's not kind of getting any better. Okay. So another way to look at this is that the number of devices that you have, the number of gates available to the system, again, is for the foreseeable future is going to grow exponentially. Okay. I think that our industry is very innovative through different technologies, through different packaging, and through different ways. We will have actually a tremendous number of devices available. Now, the hardware design productivity is kind of more or less kind of staying flat. Around early 2000s, the use of IPs, the use of memories, this kind of got the productivity up. But we are at the point where we're at an inflection point, and where we really, given the technology available, we need to see how ML is going to be changing that and getting us a big boost in productivity. Okay. So the question is, can we speed up verification by a factor of 100? Can we reduce the cost by 10x? And can we improve the quality of result by 10%? Now, 10% may seem like a small number, but it's really the last mile is the hardest problem in verification. Going from 80 to 90%, going from 88 to 98% takes the most time, as all of you who are in the verification kind of field know. And so this 10% is really, a leap, a jump to, it's a moonshot out there, right? And I think that for this, let's kind of see how can ML help us this. So hardly anyone in this room has not been influenced or is not aware of machine learning. And this actually, in the last, decade, there has been kind of tremendous advance in this area. So on the top out there is the first problem. Actually, is that of image recognition. Okay, so there's an ImageNet data set where you have actually a number of different images, and the task is to recognize what does each of these images represent. Is it a car, or is it a dog, or is it a crane? And through deep learning, through different progress, progress that has happened out there, about 2014-2015 timeframe, algorithms beat human performance. Deep learning algorithms could beat human performance. I wish this could. Do we have a pointer maybe with a red color or something? This green color is hardly showing up out here. Or this is the only pointer we have? That's the only pointer? Okay. I'll try to gesture out there. So if you look at the top, there is a zone of human performance, and around 2014-15 timeframe, algorithms could beat human performance, okay, for image recognition. Next problem is of speech transcription, speech to text. Now, this actually is a very classic problem, right? All these medical transcripts, all this conversion of speech to text happening out there. Now, this has been an area of intense research, starting with deep chip to all different algorithms, WaveNet and others. And again, actually a few years back, we have algorithms which can resoundingly beat human performance. Next problem actually comes from natural language processing. This is actually a very classic problem. You're given a passage, you're given a question, and the AI algorithm is expected to answer, give an answer to the question. Now, even in this problem, many of you are aware of techniques like transformers. Now, not too long back, about 3 or 4 years back, now we have transformer techniques which can beat human performance, average human performance, using this deep learning techniques. So tremendous progress in deep learning, and the question is, how do we leverage this out there? Now, a very quick overview of machine learning. The number of different machine learning algorithms, going from supervised, unsupervised, and reinforcement. I'm not going to go into the detail in this table out there, but illustrated with some examples. And all of this today are used in many different ways to enhance the current verification tools. And I'll run through some examples. So let's start with a brief overview of supervised learning. Essentially, in supervised learning, we have the problem is that you're given a set of training data sets. So that means that you're given some training examples. You're given actually, some labels with the training examples. So it so happens that, for example, if you have a set of images, you give the pixels for those images, and you give the label as to what those pixels represent. And the deep learning technique is supposed to, the deep neural network is supposed to learn from those images and the labels, and then classify what each of these images do. In our case, what the task here is that you find a function that can map the image to the image type. So in our case, in EDA, obviously instead of an image, this could be, for example, a verification vector, this could be a coverage point, this could be a netlist, and the label is going to be the coverage the kind of specific coverage problem or verification problem that you're trying to solve. Now, again, not every problem in EDA may have a labeled data set. So an important technique is this unsupervised learning. So taking raw data and then trying to learn from the raw data what are the different patterns in there. So given a set of vector points where you don't have any target attribute, you don't have any labels, explore the data to find what are the patterns that exist. And this data often is a multi-dimensional data with, not just not three-dimensional data, but hundreds or thousands of dimensions. And how can you kind of learn a pattern out there from this? So this is actually a fairly common situation in EDA where we have lots of data. We don't have the time or the resources or the ability to humanly kind of label this. And again, I'll show some examples of how we can use this very profitably. The last part is reinforcement learning. Everyone is, again, I'm sure familiar with game-playing machines, for playing games like chess or Go. In all of these, actually, machines have surpassed human performance. And the idea of reinforcement learning is how can you learn a sequence of steps so that you can maximize a reward. So for example, when you're playing a chess, a good move, a good step is a move that takes you towards a checkmating your opponent. And a bad step is where obviously you lose. So the whole thing is that you program into the system the heuristics that give you a positive reward for good moves, a negative reward for bad moves. Again, this is the state space is essentially almost infinite. So you in fact have to have a machine learning algorithm. You have to have a neural network kind of learn this for you. And again, as you can imagine, many problems like in verification, place route, and others can very profitably benefit from reinforcement learning. So in all of these different areas, whether it's static, formal, simulation, debug, or even hardware software acceleration, these techniques have been kind of used in a very effective manner. The question is that how do we improve QR, TTR, and COR? And it's a good idea to start off with, what is the percentage of bugs found? So in static, formal simulation, about 10% of the bugs found through statics verification, 20% formal, 65% simulation, hardware software acceleration for the last 5%. And the further down the design cycle you go, the more expensive it is to find the bug. And the goal with machine learning is how do we kind of shift all this left? How do you kind of get these bugs discovery earlier in the cycle? So question is actually what makes this so complex? So let's kind of take some numbers to get a perspective on this complexity. So if you have 100 billion transistors, and let's say that you have about a billion state elements, the number of states alone that you have is about 10 to power 300 million. Now just for comparison, the number of atoms in the observable universe, right, is about 10 to power 100. So the kind of state around, the kind of transitions we're talking it is huge out there, much bigger than anything else that exists in our physical world. So the challenge out here is that there are diverse set of verification formats, tools, and flows. So there's no ImageNet, right? So ImageNet, the first problem, machine learning problem, I told us that you have this set of images. In over a year, a lot of academicians worked hard, kind of created this carefully curated data set out there. But the problem in our industry is that there are a lot of different diverse verification formats, tools, and flows. It's not just verification format tools and flows that change. There are a lot of different design types. Every design is unique. So you have C++, system C, system Verilog, assertions, covers, reports. Every tool has its own internal representation, right? There's no verification ImageNet. There's no standardized data set. And I think there are about 300 to 400 different representations and steps in the EDA flow. How do you kind of get this? The data size is highly variable. Every design is unique, and there's no fixed size images or word embeddings. And one other problem, actually, this is actually an important thing, is that for performance, for verification, running verification at speed, these machine learning algorithms, not just training, but even if you train them, you have to do inferencing. So inference speed is very important. So if you're expecting to, for example, run through 1 million cycles per, million cycles out there, and every cycle takes a few milliseconds in inferencing, so you have already kind of taken this into a few million seconds out there, a few tens of thousands of seconds. So this is again an important part to kind of take into account. And I'll be talking about some of this out there. So let's see, how do we start off with this shifting left out there in this simulation world? So if we take on the y-axis, we have this coverage. On the x-axis, we have this time. Simulation through manual and random, kind of gets us plateaus very fast. If you do constrained random, that gets us, closer to the coverage target. And with AI, the expectation is that we should be able to kind of do this, a shift left, where we can get to the same results faster, but get improvement quality of results. And of course, the cost of results is going to be better because, because I think that you're saving on this compute resources and by getting to the same results faster out there. And I think about 80 to 90% of a typical data center cost for a design house is in fact the compute infrastructure for simulation. Okay. So let's see, what does VCS do today? So VCS is our flagship simulation engine. And what does VCS do to kind of do this? So I've kind of illustrated this with what the state space exploration problem is. So let's imagine that if there's a design, you have each of these dots which represent states. You can go from each state to any other state except that you have a few illegal transitions. Now, you have a set of coverage targets. Each of these dots have been marked with as a coverage target. And these coverage targets, of course, are specified by your targets and tests that have been specified to VCS. Now, given this constraints, targets, and test, you can kind of go to and get to the kind of desired targets and cover them. But what happens is that, and you might discover some holes, discover some bugs, but actually a number of verification coverage holes can kind of remain. Now, what we have done as a part of a verification space optimization is that we can add some compute, throw in some machine learning algorithm, and using AI and using information from the coverage holes, we can let VCS, verification space exploration optimization, go and explore additional states and discover additional bugs out there. And this has been actually very successful with real-life designs, and this is actually, in fact, an example from a real mobile application processor. So traditional constrained random simulation, with about a number of test seats and passes, took about 1,000 passes to reach the target. Using this AI-assisted verification space optimization, that coverage target was not only achieved much earlier, but with much better performance. And the time to results was reduced from days to hours. And in fact, with some more runs, the coverage could kind of exceed target. So about an order of magnitude in about 10 to 20x improvement in the coverage using our VSO.ai solution. So go to the website. I think that we have some very nice information out there and some kind of nice technical matter that you'll be able to see. Let's go to kind of static verification. So structural and functional sign-off checks. I mean, this is actually one of the mainstays of verification as you start verifying a design, as you get started with a new design. This includes a broad set of checks, including power intent specification checks, clock domain verification, reset domain, language checks. The problem is that it's not uncommon for a block or for a SOC to kind of get between 10,000 to a million violations. Man, it's just there. You write your UPF or you write your SDC verified design, boom, you get a million violations. Now, what do you do with that? So this is actually a real life chip, actually a customer chip, and I think we have about 345,000 violations. Where do you start? So, static product, this VC static product actually has made a number of innovations in this area using machine learning and using unsupervised learning and using actually a set of sophisticated clustering algorithms, hierarchical multi-phase clustering algorithms. It can neatly classify these violations into a number of different clusters, find out the cause-effect relationship between the violations, and can help you with automated divide and conquer. And this can reduce your problem effort of debugging this and finding out where to start with this violation by a factor of 10 to 100. So there's a mobile SOC, and using Spyglass CDC, the number of violations is about 100,000. After ML, EDA, and clustering technology, this got reduced to what, only 102 clusters to kind of analyze, right? And let's take a real example, actually. So the user specified, a create clock out here at this point, a create clock at this point, and the number of violations that came out from this alone was about 12,000 violations. Because clock 1 and clock 3, clock 2 and clock 3 are not really asynchronous. Now, the traditional approach would have been to kind of look at each of these violations one at a time. Maybe, if you're expert, you might be able to kind of cluster this. But now you are using our, hierarchical clustering technology. We could immediately kind of classify these and get to the point that these 12,000 violations are related. And if you identify the root cause for one of these, you'll pretty much get all of these, okay? And so 10 to 100x reduction in the violations for analysis, you identify the root cause of violations and minimize the human waivers. Now what enabled us to do this was that, of course in our tool, we have access to all of the internal data structures. We could compute the appropriate vectors, we could kind of weigh them. And it's not something that you can really do out of the tool. You cannot write log files into that. And that kind of enabled us to kind of get this kind of big gain in quality of results and time of results. So as opposed to manual analysis, which kind of takes, for a million violations or 300,000 violations can take a long time, we could kind of get to, this violation analysis very, very fast out there. Another problem that we kind of, where machine learning has helped us is in our formula verification solution. We have actually, a VC formal is our flagship formal product. And I think that for the audience, I can tell you that this has one of the fastest performance, of all the verification tools in the industry. If you haven't yet tried it, you should try it. And one of the problems with formal verification is this tries to solve some of the hardest, most computationally intractable verification problems that we have in the verification industry today. Essentially, you have your design, and you want to kind of take this assertions, P1, P2, or P3, these assertion 1, 2, and 3 are system Verilog assertions. And you want to verify these assertions for this design block and verify it comprehensively under every state and input and every kind of combination out there. Now, this problem, if you look at the complexity of what it takes, there are about hundreds of thousands of properties. We have about 30 plus solvers engines. We have a fixed number of machines. We don't have the luxury of infinite resources. We have limited time. And there are numerous things a user has to do. So with this kind of stats, it's not unknown to kind of have this tool kind of run for days. And obviously that again does not quite work. So we have used ML optimization to look at the properties, look at the designs, order that and orchestrate these appropriately so that these can be dispatched to formal engines and get to run things fast. So a way to kind of look at it is we have this regression mode analyzer. It looks at the execution, it looks at execution runs, learns from that using reinforcement learning, so that when you have following execution, it knows the path to take and it optimizes this. And this actually is a great example, right, where as this tool runs on designs, the orange is the initial run, the red is the AI optimized run. And you can kind of get about 10 to 100x speed up by using our RMA technology. And this can help. This performance has been seen across board for all kinds of designs and all kinds of application processes. And if you look at the number of properties verified, this gets us to, rather than default scheduling, we can kind of get to better time to results, better quality of results, better quality of results, and obviously better cost of results are there for formal verification. Now, getting on to debug. Now, for every task, every verification task, whether you're running a static or simulation or formal, you have to end up debugging this. Now, a design can have, billions of signals. Obviously, every simulation run can have, millions of cycles. So now, where do you trace back if you have a violation, where do you trace it back to? In time and space. Not only, which signal to see of these billions of signals, but where do you see that in the time frame of there? And Verdi, our flagship verification tool, has built many of these capabilities for advanced root cause analysis. Now, looking at past simulation results, looking at user flow information, debug action graphs. This information, all of these goes to our ML database and using a combination of supervised and unsupervised learning. It can do this analysis, identify the top root causes, give you the top debug actions, and let the user zoom on to the region of interest and debug design faster. Again, successfully used in many real-life designs. So this gets us to a shift left with quality of results out there for debug as well. So now, using machine learning, all of this gets us back, with all of this example, you can see better QR, TTR, COR, and it's getting us closer to this where we want to kind of realize, our verification goes through machine learning. Another actually very interesting application I wanted to talk about was this circuit specification to system verilog assertion translation. So NLP techniques, as you know, are becoming more powerful every day. Everyone would have heard of GPT-3 and transformers and all this. And problem today is many verification items or verification artifacts start off with this English descriptions. Now, translating this into system verilog assertions is a very painstaking manner. So what if we could put a bit of structure to this English description? So we have devised a flow where we can take this English language description, read these, and in fact generate system verilog assertion. User has the capability to kind of give feedback, and as you kind of do feedback, the tool learns the quality of the assertion author, and then kind of improves in quality. And actually, this is something that, given this input English, actually these kind of English language sentences kind of get translated into output system verilog assertion. It's a pretty nifty tool that is still prototype, but it has been kind of worked on, actually used on several large designs. Another problem related to verification is how do you select test using machine learning? It's not just enough to kind of improve the core algorithms, but if you're checking in a design and you have, let's say, a smoke test, 10,000 smoke tests, it could be very expensive to run this. You might have to wait for 20 minutes, half an hour to kind of get through these. But what if you needed only 10% of the tests to kind of really pass through the specific design modification you made? So this is a part of our test selection process using machine learning. So throughout the RTL data process, we keep track of the design delta changes. We have information about the design representations in our tools. And using that, we craft a set of features that we can kind of give you a verification confidence for this quick regression runs before I check in, get you about 90% accuracy, 90 percentile accuracy, as opposed to running the full test, by just running a tiny fraction of the test. So another pretty nifty, nifty application of machine learning out here. So question is, can we improve the verification speed up? Can you speed of verification by 100x? Can we reduce the cost by 10x? Can we improve the QR by 10%? Absolutely, the answer is resounding yes. We have done that today, and we hope to kind of do even better in the future. Now, where does all this kind of take us there? So in the last, in the last 10 years, there have been a lot of advances in machine learning. But applying this machine learning techniques to ED and to verification problems is not simple, actually. So we have leveraged our deep understanding of the problems and deep understanding of ML algorithms to achieve this across the full gamut of problems, across formal, static, dynamic, and debug. This is something we have taken this to design specification, authoring of assertions and specifications, optimizing runs. We have given orders of magnitude gains, speed up, reduction in cost, improvement in quality of results. Now, this kind of positions us well to go to the next, next era of 24-hour design cycle. This is ERI idea, right? So these are DARPA and other funded initiatives. How do you kind of verify these design in 24 hours? So you need to kind of have breakthroughs in design and verification artifact representations. We need to go beyond our current RTL-based verification approaches. We need protocol language models, we need architectural language models, we need semantic design representations. And what we have done today gives us a good place to start off in moving towards our vision of 24-hour design cycle. Okay? So thank you.
Thank you, Mr.
So if there's time, I think I'll take some questions.
Yes, please. Any questions from the audience?
So I have a question. As in, unsupervised learning is okay, but for supervised, how do you get enough data to actually tune your engines to work?
So yeah, so supervised learning is a bit tricky in the sense that you'd have to kind of create label data, okay? So that means, for example, so one of the problems is, I'm going to give a very specific example. Let's say state machine complexity. Is it a complex state machine? Just a yes/no answer to verify. So one way to do it would be, for example, for a human designer, human expert to look at each of the state machines, right? Look at the Verilog descriptions and manually label it. But as you know, that can be pretty expensive out there, right? As designers and verification engineers, we don't have time. So, there are different ways you could do this. You could kind of, for example, do a full simulation of it, exhaustive simulation, so that definitely during this data set creation time, you can throw a ton of compute. It might take hundreds or even thousands of hours kind of compute this. But once you generate this automatically, right, then in that case, then you could use those models at runtime to efficiently make those, to do this inferencing and do this. So runtime is one of the places where data set automation can be done. But for many other problems, unfortunately, there's no other way around than to manually kind of doing this. There have been some university research initiatives in kind of creating this. But given the diversity of the data and design representations, I think that's a pretty tall order. So therefore, I believe that actually semi-supervised, transfer learning, reinforcement learning, unsupervised learning. So these will be the dominant tools that will be used for, used in the verification industry today.
I have another question. So what has been your experience in all the companies, right? IP specific and their design specificity. So what has been your experience in, let's say, learning from Samsung to, let's say, NVIDIA? What is your vision and how do you see that going? Because
Yeah, so the question is, what is about the differences in designs in different companies? Now, I think actually is that if you look at the fundamental building blocks, right? If you look at the level of state machines, the kind of coverage problems, these problems are fundamentally the same. But if you have a large, processor array, like for example in a GPU, versus if you look, for example, actually at a low power design, let's say that, for a mobile SoC, there are certain differences in characteristics, there are certain differences in power and all that. So there are some differences out there, but I think the expectation is actually for a machine learning algorithm to be useful, you did have to have training data sets or use cases that could handle all of these. So fundamentally, we recognize that differences, but we have worked on generalizing our algorithms that it can handle across this design spectrum.
So my question is more about, let's say you learn from one semiconductor company. How do you ensure you can apply it another semiconductor company? Because there is a lot of IP and those kind of concerns involved, right?
See, the thing actually is that a lot of the enhancements that we do not expose any kind of IP. I'll give you a very simple example. Whether it's formal or simulation or static, right? You might go to company A, you have some performance issues, you improve the tool performance by studying where the tool bottlenecks are for a specific kind of graph, and you put the general enhancement of the tool, okay? So just because you take that, you can take the tool and go to company B and its simulation speed or formal verification speed, so it does not mean that IP leakage is happening. So think of machine learning in that way. If you improve your, if you can get information where you can improve the performance of the tool, where you can improve your models, then that's there. But if the question is, if you're taking features and data sets that are extracted from company A, you get that back, for example, let's say to Synopsys, for example, and then you kind of do this tuning. There may be some concerns, but that is something that industry as a whole to resolve, and we don't follow that practice today. And I don't believe any other EDA vendor does that also today.
Thank you.
All right. So just to be very clear, we are very, very careful with how we handle IP, and we ensure, it's our responsibility to ensure there's no IP leakage that happens.
We have time for one more question.
Hey, hi, Manish. Hello. So my question is, you mentioned that there is a 10 to 100% improvement in the speed, right? So in the overall verification design cycle. So what is your reference? I mean, you are considering the verification window to 1 month, 2 months, or what is the baseline?
So the question is, when I say 100x, what's the baseline that we are kind of comparing it to?
Right.
It's really the latest version of the tool with, without ML and with ML, right? So that's the kind of thing out there. So when I talk, for example, about formal performance, it is formal verification, for example, without our RMA technology, and formal verification with RMA technology. So it's not that we're comparing it to an old version of the tool, because even natively out of the box, our tool from release to release sees 2x, 4x, 10x improvement. So we are comparing it to the baseline out there with the version of the tool with ML and without ML.
Yeah. So if we just measure it in terms of months, right? So your baseline, let's say it's 3 months verification cycle on a design, and then you are using the ML. It shows an improvement of 100x on that.
So the thing actually is, for example, I can give you a very specific thing, actually, for example, for VC formal. So if you take a VC formal release, actually this is kind of September, I think that we had a major release in July. You can take that July release, run it on a design. You can take that's the very same release, run it with the ML flag enabled on. The speed up that you'll see is about, on many designs, can be 10 to 20x, if not more, right? And again, I should tell you, this is an average speed up. There'll be some designs in which you'll see 2x speed up, some designs in which you see 100x speed up, okay? That's very much design variable, but yeah, that's the kind of performance gains that we see.
Okay, thanks.
Sure.
Thank you for the session, Mr. Manish Pandey.
Right.
I'd request Pradeep to give him a token of appreciation to Mr. Manish Pandey.
Right, thank you.
Thank you very much.
Okay.